Hello and welcome everyone. So let's start off by looking at a problem like this here. So we have a diagram, as you can see here. We show a circle O. The measure of arc AB is 4x here, so I'm going to go ahead and measure that. We're told that this is 3x minus 1, and angle A is 6x plus 12. We want to determine the measures of all three angles of the triangle. Okay. So note that we have two of the angles of the triangle, which is often a good thing here, but we don't have the third. However, remember here that AB, as you can see here, is 4x, and notice that we have AOB, which is a nice little central angle. So if you recall from yesterday's lesson here, we mentioned how the measure of an arc is tied to its central angle here. So we have the central angle like so. So at this point here, we can see that this is our 4x. Therefore, the 4x can be moved in here as well. So we know that the measure of arc AB being equal to 4x here, that implies the measure of angle AOB is also 4x, and that's going to be the key to solving this problem here, because now we can put it all together. We now know that 4x plus 6x plus 12 plus 3x minus 1 is equal to 180 here, so we can go ahead and do that. This looks like 13x plus 11 equals 180, so you get 13x, I think, is 169, and therefore x is 13, because 169 is 13 squared. So now we can go ahead and fill everything in here, right? So we know this is going to be 3 times 13 minus 1, which I think is 38 degrees. There's going to be 4 times 13, which is 52 degrees. And then finally, there's going to be 6 times 13 plus 12. Well, 6 times 13 is 78 plus 12, and that yields us a 90-degree angle. Okay. So, nice. So notice that what's going on here, ladies and gentlemen, is that we have this sort of situation here where you have your line. Now let's focus on this here. We'll see that AC, one of the things you may notice about AC is that, well, it's not complete yet. Let's continue drawing it. So if I were to continue like this, right, AC would go out like so. So one of the things you may note about AC is that it hits the circle here. It hits the circle at that point A and then never hits it again, right? It hits the circle exactly once here. So in this situation right here, we have this here is what is known as a tangent line here. And this is a term that's going to be used throughout here. We can have tangent lines of things that are not just necessarily circles, so other curved objects as well. So we can mention this here, what is known as a tangent. So we can say that a line is a tangent to a circle if and only if it intersects that circle exactly once at the point of tangency here, right? So the point of tangency is where the circle hits the line. So the line hits the circle. So this here is going to be our point of tangency. Okay? Now, you'll note, wait a minute, shouldn't OC do the same thing as well? Shouldn't OC be a tangent line as well? Well, one thing to note about OC is that, well, it's not a line yet. It's just a line segment. If we were to extend the line like so, oh, I drew that really poorly, but you get the picture here. You'll note that this line hits the circle again at another point here. So this line actually hits the circle exactly twice as opposed to exactly once here. And that, in this case, we refer to as what is known as a secant. So we refer to that second thing here as what is known as a secant. A line is a secant to a circle if and only if it intersects the circle exactly twice here. Okay, so we call that a secant line. So in this situation here, OC is a secant line and AC is a tangent line here. Okay. Now, one of the first things to note about a tangent line here is something that you may have noted here. We noted this is a 90-degree angle here, which implies that AO and AC are perpendicular. We have right angles here. Now, this is no accident, ladies and gentlemen. It does seem like this is going to be the case here. And this actually leads us to an important theorem here, probably one of the most important theorems about tangent lines and circles. We end up with this here. So we can say that if a line is tangent to a circle, then it's perpendicular to the radius of the circle drawn to the point of tangency. Now, this is a difficult theorem to prove directly here, right? Trying to do this directly here is going to take us a little bit of time. So what we're going to do here is we're actually going to show that this is going to be done by contradiction. I'm going to do this as a proof by contradiction. Okay, so again, let's draw the picture here. So we're going to have a tangent line like this here. So let me draw a tangent line like so. So let's say here, this is my point of tangency. Let's call it P here. Here's O, right? So we're going to be given, and I guess I'll call this here line L. Line L, in this case, is tangent to circle O. I want to prove that line L is perpendicular to OP, okay? So we're going to prove this particular theorem here. Now, this is going to be a pretty straightforward proof by contradiction here. So what we're going to do here, as any proof by contradiction, we're going to start by assuming the opposite, right? So we're going to assume L is not perpendicular to OP, right? So L and OP are not perpendicular. However, there is, so even though L is not perpendicular to OP, there is a point where you create a perpendicular, right? Because you can draw a line. This is a line L, and this is a point O. We know that it's possible to construct a line through a point perpendicular to a given line. And if it doesn't hit it at P, it's going to hit somewhere else. So let me call this point here. Let me say it hits at the line at the point Q, and we'll do that here. So let's say here that this OQ is going to be with the foot of my perpendicular. So we got right angles here, right? Thus, there exists some points Q on L so that PQ is perpendicular to L. I'm going to draw it. Now, this picture may look a little uncomfortable to you, and you're right. This doesn't look like a right angle here, and we're going to see why that's the case. So now what I'm going to do is I'm going to draw in OP as well, right? So let's look at triangle OPQ, right? So in triangle OPQ, so we note that, wait a minute, this is a right triangle, correct? This is a right triangle here. So notice that because it's a right triangle here, well, we know that the right angle is the longest side. The right angle is the largest angle in the triangle. So OPQ is the right angle here. So we know that in this case, OP is the hypotenuse, right? Because it's opposite right angle OQP. The OQP, sorry about that. And therefore, one of the things we know about a hypotenuse of a right triangle is that it's longer than every other side. So that means OP in particular is greater than PQ, and it's also greater than OQ, right? So because of the fact that OP is a hypotenuse, we know OP is, lives up to its name. It is indeed OP here, and it's going to be bigger and more effective than anything else here. In this case, OQ. Now wait a minute. There's also a bit of an issue here with this, right? Because if you take a look at what's going on, notice that in this situation here, L intersects the circle once, correct? Because that's what a tangent line does. It hits a circle once. So this implies that Q is outside the circle. Because if Q were inside the circle here, that means this line would hit the circle again. And I think you can show that intuitively here. Now, if Q is outside the circle, that means that it's more than the fixed distance away, because OP is a radius here, right? Because P is on the circle. This implies here that OQ is greater than OP here, right? Because OP is a radius, and Q is outside. So I've just shown here, by argument, that OP is bigger than OQ, and OQ is bigger than OP. Wait a minute. How's that possible? I have now shown that there exists two numbers, two lengths, such that A is bigger than B and B is bigger than A. That's not possible. That's a contradiction, right? You can't have that happening here. So notice that this is a contradiction. So I'll go ahead and label this here. This is a contradiction. Right? This is a contradiction here, ladies and gentlemen. Thus, the assumption is wrong. So we know that L is perpendicular to OP. And we're done. So as you can see here, this proof actually works out very nicely here. It's just a straight up proof by contradiction, and it works out very, very nicely here. You have something that looks like this.